what is a cryptographic hash function? Here we have the diagrammatic representation of this scheme. It uses the original message. The compression function is it is made from scratch. We use the message digest. Rabbin scheme is the improvised version of the Damgard scheme. Hello students, welcome to the next session of Network Security. I am Dr. Soumyashri from Department of Computer Science, Vidhyaashram, first grade college. Let's start this session. In this session, I am going to tell you about the concept in the 4th unit, that is the cryptographic hash functions. Okay, let's start this session. The first thing is, what is a cryptographic hash function? The last units that we have discussed is all about the cryptographic methods that we have used will ensure one of the security goals, that is the confidentiality. The goals we had is the confidentiality, integrity and availability. The second and the third unit concepts were all about the confidentiality, how to maintain the confidentiality of the data from the adversary. Next goal we need to reach is the integrity of the data. What is integrity is, it must retain its state whatever may be the condition. Adversary must not change the state of the data, isn't it? State of the plain text. The condition of the text must be maintained starting from sender to receiver. We know about the possible attacks that can happen over a integrity of the data, isn't it? So we know about the possible attacks that can happen over the integrity, like the modification, masquerading, replaying and the repudiation, that is changing the current condition or current state of the data, modifying it or impersonating the identity of a person. So it is all about the integrity. So the main goal of the hash functions or cryptographic hash functions is to ensure the integrity of the data. Integrity is nothing but the accessibility must be only to the authorized person in an authorized mannerism or authorized method, isn't it? So this will be ensured by the one of the goal, that is the integrity. For maintaining the integrity, we use algorithm or a method known as cryptographic hash functions. What are these cryptographic hash functions? Before knowing more about the cryptographic hash functions, let's know what is this hash function. So cryptographic hash function is an algorithm, okay? This is an algorithm. Why do we use an algorithm here? Suppose you have a sender or you have a person who is preparing a will, okay? That will be maintained in the advocate's office. You need to maintain the integrity of the will that only the authorized person, say he is an X, if you take the person X is the authorized person who has prepared the will, who is the owner of the property and prepared the will for protecting the property. So that will must not be available to anybody else who are not authorized. Only the person who has prepared the will must be able to change it. How does, if somebody else copies the will and says that he is the one who has prepared this will, the Y, who is an attacker or an adversary, has prepared another will and says that he is the will which he has is the original will, whereas the X, who has prepared the will, and the will prepared by X is not the original one. The will prepared by Y is the original one. If the Y proposes that the will he has prepared is the original, how do you ensure that the will prepared by X is the original? He is the original owner of the property and he is the authenticated person who has prepared this bill. It is the original bill. How do you ensure that? So for ensurement, for maintaining the integrity of that will, you have to prepare a method which tells that the will prepared by X is the original one, not the Y. Then for this, what you will do is, you will prepare a biometric method to ensure that or to confirm the original will. What you will do is, when X prepares a will, you will take the fingerprint of the X over the document. On a document, you will take the fingerprint of the X, which tells you that the will which has the fingerprint of X is the original will, and the will which doesn't have the fingerprint of the X is the fake will, which is not prepared by X. When Y gives you a will with his fingerprint or any fingerprint, what you can do is, you can compare the will or fingerprint in the will with the fingerprint of the in the original will. When you compare those, if it doesn't matches, that means the will given by Y is not original. He is changing the integrity of the data, isn't it? Or integrity of the will which is prepared by X. So this is the original form, or the document and the fingerprint are the records that will be maintained in the manual form. What happens if that comes to a computer? Say if it is a message. Instead of will, we take the message. Message sent by a sender. If an adversary sends another copy of the message, changed message, to Y, we have two sender and receiver, X and Y. X sends a message to Y, which is taken by an adversary Z. Okay, Z changes the message, say X0 as the message. The adversary Z captures or gets the message X0 and changes it to Z0. And Z0 is sent to Y instead of X0. Now, after this, X0 will also reach Z0 and X0. Both will reach the receiver. How does the receiver confirms that the X0 is the original message sent by X, not the Z0? How the Y is going to confirm? For maintaining that integrity of X0, we use the hash function. Okay, so here we have the document, that is in normal word, we use the document, and document confirmed with fingerprint. This is the method that we follow in the real world, isn't it? So real world document and fingerprint will be replaced by the message in the computers. So document is replaced by a message. Okay, it is the message sent by a sender. We'll have a message digest. We use a term called message digest, or simply digest, to give the format of an original. To maintain the integrity, we confirm the document with the fingerprint. Like that, message will be confirmed with the message digest, where for getting the message digest, we use the algorithm hash function. Cryptographic hash function will be used to get a message digest from the message. Then what does this hash function is all about? What does the hash? So message is a variable. Message with variable length will be converted to message digest with fixed length. So we'll have a message with variable length will be converted to message with fixed length, which is called as the message digest. The value or this fixed length value is called as the hash value. The fixed length value which we get by executing the hash function is called as the hash value or simply the hash. Okay. So the algorithm which generates the hash value or hash is called as the hash function. If it is applied to the crypto system, it is called as the cryptographic hash function. So what does the cryptographic hash function algorithm will do is, it will generate a hash value. Hash value is the fixed length obtained from the variable length. Okay, variable length will be converted to fixed length. That fixed length value is called as the hash value. So the cryptographic hash functions generate the fixed hash value. Okay. With this basic knowledge of hash functions, let's move on to the concept to study about more about the cryptographic hash function. Okay. So cryptographic hash function takes a message of arbitrary length, that is a varying length or the arbitrary length, and creates a message digest of fixed length. So this message digest is called as the hash value or simply the hash. It is called as hash value or simply the hash. Okay. So the ultimate goal of this unit or this concept is to discuss the details of the two most promising cryptographic hash algorithms. There are two different cryptographic hash algorithms that are used to ensure the integrity. They are SHA 512 and the Whirlpool. There are two algorithms. We are going to discuss these two algorithms in this concept. Okay. First thing is the iterated hash function. So iterated hash function is going to do iteration of the fixed length inputs. Okay. So the general method that we use in hash function is taking a variable length or arbitrary length message and as the input and taking a fixed length output. Instead of that, the iterative hash function suggests that or proposes a concept where instead of variable length or arbitrary length, we'll take the blocks of the arbitrary length message which are fixed length input will be taken in kind of a block, fixed length input will be taken and algorithm is applied to fixed length input as an iterative operation. Continuously or iteratively we are going to execute or we are going to use the hash function algorithm on fixed length input, which is more convenient than using the arbitrary length message. We'll use the fixed length input and we apply the algorithm iteratively to get the fixed length output for the message. Okay. So for this, we make use of a scheme known as Merkle-Damgard scheme. So it is a special scheme that is used to get the fixed length of input and get a compressed function. So here arbitrary length of message will be compressed to a fixed length. Okay, not all the bits are used. Some will be truncated and only fixed length will be used by compressing the variable length, or the arbitrary length message will be compressed to fixed length. Okay, in this we use a Merkle-Damgard scheme to perform this operation. Here we have the diagrammatic representation of this scheme. It uses the original message and the padding, the length of the message that must be used. So this scheme uses an iterated hash function that is collision resistance. Collision resistance is, in hash function we use 3 steps. One is the cryptographic hash function. The basic thing is cryptographic hash function must fulfill 3 criteria. One is the pre-image resistance, second pre-image resistance, and the collision resistance. So we use these 3 things, that is pre-image resistance, second pre-image resistance, and the collision resistance. So pre-image resistance create a copy of the message. Whereas second pre-image creates another copy of the same message but with a fixed length. So second pre-image ensures that the adversary will not create the second image of the message of variable length. So it will not allow the adversary to create or forge the message that is created as a pre-image resistance. Okay, the collision resistance is all about avoiding the 2 copies of the same message. So the thing is, the hash function must be pre-image resistant. That means there must not be any chance for the adversary to create the copy of the original message. The original message authenticated user can create the copy, but the adversary must not be able to create the copy or forge the copy. That is why the pre-image resistant and second pre-image resistance will be checked, where the adversary will not be able to create a copy or forge the same message and change it. The collision resistant criteria says that the hash function must not get the 2 messages or get the messages from the adversary. It must not collate with the 2 messages, because hash function will create a hash value, isn't it? A digest. So the adversary can create a new value, new hash value, which collides with the original. The hash function must be able to recognize the original digest that is created by the hash function or the algorithm. That is called as the collision resistance of a hash function algorithm. So the Merkle-Damgard scheme ensures that the algorithm must become the collision resistant. In this, we have the diagrammatic representation where we will have n bits of m length, m1 of length n bit, m2 of length n bit, and mt of length n bits. There will be the messages, the message digest, which are compressed with from the original message. We get the message, fixed message blocks which are compressed with the original message. When you get the original message, it is compressed to n number of bits and are given to the compression function. So there will be hash function which gives the message length m to the compression function. There will be separate compression function which compress these blocks or which compress these length message of n bits, which gives a hash value h1, h2 up to ht minus 1. We get the hash values from these block of fixed length or fixed length input and gives you a message digest of m bits. Okay, so this is how you can iteratively, you are using the same compression function iteratively for all the m set of values or m set of messages, which gives you a message digest of m bits. Okay, so this is a scheme. Then we have the two groups of compression function. We use two groups. The compression function is, one is, it is made from scratch. We use the message digest with getting the message from the scratch, and we have a symmetric key block cipher that serves as a compression function, that is the whirlpool. So we use two algorithms, that is the message digest with SHA 512. Another compression function we use is the whirlpool. Now we compare the SHA MD5 and RIPE-MD algorithms with respect to digest length, the basic unit of processing, number of steps we need, maximum message size one can get, primitive logical functions we use, additive constants that are used, and the endianness, that is the method that we use to represent the bits, whether it is little endian, big endian. So that will be compared with each of the algorithms, hash function algorithms. We have these many comparison of the different parameters. Okay, so we have the relative performance of several hash functions. Okay, we have the MD5, SHA1 and RIPE-MD. So whirlpool, which will be relative performance it is giving, how many Mbps it is using. MD5 uses 26 Mbps, whereas SHA uses 48 Mbps of data, and RIPE-MD uses 31 Mbps. Okay, so along with that, we use the characteristics of secure hash algorithms. That is, the SHA stands for secure hash algorithms. We use the maximum message size to compare different variants of SHA, that is SHA1, SHA224, SHA256, 324 and 512 or 512. So we have various versions of the SHA. We can compare the characteristic of each secure hash algorithms with respect to maximum message size. They can create the block size, they can create message digest size they generate, the number of rounds, iterative, as I said, iterative functions. That means iteratively they use the same function, compression function, and the word size they use. Okay, so the maximum is the 64-bit they can use. So we use the SHA 512 algorithm to compress and get the message digest. Let's look at the Rabbin scheme. Rabbin scheme is the improvised version of the Damgard scheme, where we use the block of m length and the m bits of previous message digest. So it is the message digest from the previous message. So we use the message digest. So this is the Rabbin scheme, where the M block of key acts as the key for ciphering. Instead of the compression function, we use the encryption method or encryption algorithm to get the ciphertext. So the previous message digest will act as the plain text and the new message digest will act as the ciphertext. Okay, in this form, we take the message digest from the previous message as the plain text for getting the message digest. The cryptography or the ciphertext we get is the new digest. So this is how you can use the cipher algorithm, encrypt algorithm to get a new message digest. Okay. Then we have another scheme, that is Davis-Meyer scheme. This is same as the previous one, that is the Rabbin scheme, but it is improvised that you can observe here. You can have the same message block as the key that is used to get the ciphertext. Again, the message digest from the previous message acts as the plain text. Same encryption cipher method is used or encryption algorithm, and for the new digest will be taken as the ciphertext, but the modification what has been done by Davis-Meyer when compared to the Rabbin scheme is that the message digest is ORed with the new ciphertext to get the new plain text. In the Rabbin scheme, they haven't used the previous digest, but in the Davis-Meyer scheme, they are using the previous message digest XORed with the ciphertext. They are using the XOR method to get the new plain text. So, same procedure is made to get the new message digest. Then we have improvised version of the Davis-Meyer scheme, that is Mathias-Meyer-Ossis scheme, where they uses same concept, plain text, key as well as ciphertext with a padded message of T blocks. This time, this is also used for XOR. So, message of M block, the previous message digest as well as the new ciphertext will be added to this scheme. So, this is how you can get a new message digest. One is the previous improvised version of the previous method of getting the message digest. Then we have another improvisation, Miyaguchi-Prenil scheme. So, they use the same method, okay, for getting the message digest. All right. Then we have one of the algorithm that we have used is the SHA 512. It is the algorithm that we generally use. It is the version of SHA with a 512-bit message digest. The length of the message digest will be 512. Okay. So, we have the hash algorithm, that is the SHA algorithm, or you can call it as the safe hash algorithm or secure hash algorithm, which uses 512-bit of message digest. This version of SHA algorithm, like the others, is based on the Merkle-Damgard scheme, that is getting the fixed length of input. Okay. Here we have the message digest creation representation of the SHA 512. We use 1024 bits as a message block. In fixed length message input has 1024 bits or 1 GB or 1 gigabytes of size will be used for each of the block. Each block is applied to a compression function. It is applied a compression function to 1024 24 bits of message with 512 bits initial value, which takes a compressed value of 512 bits. Each block will get a fixed length output of 512 bits, which are taken as a message digest for the original message. That is the augmented message. We have multiple of 1024 bit blocks. We have this. So each 512 bits is fed to the compression function with 1024 bits. So this will be used 1024 but plus 512 bits is applied to the compression function, which gives you a compressed value of 512 bits. Each bit is applied to the next block to get new message digest of 512 bits. We have total message digest of 512 bits at the end of the compression function. We have the message preparation in SHA 512. The SHA 512 insists that the length of the original message must be less than 2 to the power of 128 bits. Okay, so it creates a 512-bit message digest out of a message length less than 2 to the power of 128 bits. So we have this representation of padding and length field in SHA 512. Length must be less than 2 to the power of 128. This is the original message we get. The variable length will be padded from the original message. We get multiple of 1024 bits out of the original message. Okay, we use the words for representing a message block, and the digest will be represented as the words. How many words you can use is 16 words. Each of 64 bits will be used, which make up 1024 bits. We use the message block with 16 words, each of 64 bits. Okay, so each block contains 16 words. Each bit of or each block of 1024 bits again represented as 16 words. Okay, and we have the message digest of 8 words, each of 64 bits, which make up for 512 bits. Some 16 words, total 8 words of 512 bits will be made by the SHA 512 algorithm. Okay, how does the word expansion is in the SHA 512 is, we use block of 16 words which are made into 8 words of, that is word 79. We use the rotation shift function to calculate or compress the functions. We use these expression to compress the functions, or this is how you can expand the word. These are the expressions that are used to compress the word. Okay, we have the message digest initiation in this table. This is how you can represent the message function. This is about the SHA 512 algorithm. In the next session, I am going to tell you about another algorithm, that is the whirlpool algorithm. Thank you.